Yeah, yes. Is that fine? Yeah, that works. Yeah.
Okay, so I guess we can start. So it's a pleasure to have with us for this morning session Thomas van Riet. He's going to give us a review about the status of the citr space in string theory.
Well, the pleasure is mine. Thank you very much. This is, I guess, for many people, the first in-person conference. So it's nice that it's on a beautiful island. So thank you very much for the invitation. Yeah, I'm going to talk about a sort of complicated topic for many reasons. And I thought this would be a nice illustration of this topic. I want to start with a disclaimer, is that I think it's impossible to give a fair review on the status of the citr space in less than 6 hours, and I got 60 minutes, or probably 55 minutes. I should also say the difficulty with giving a review like this is that the citr constructions rely on moduli stabilization. So it requires you to give a review on moduli stabilization, which I will not do. I will specifically focus on the SUSY breaking part to get to the citr space, say from ADS. And I'm sure I will mention my own work way too much. Okay. So I will talk about 4 things. And the first might be for sure too easy for many people, but I like it for myself. And these are the general ideas behind this program of trying to find the citr space in string theory. Because you should, when you think about that question, I think there's already a why from the start. Why should one even do this? Then, because we're, it's 2021, you cannot mention the citr without mentioning the swampland program. So I'm going to start with this, okay? When it comes to the new things about the citr space. Then specifically, I will go to what many people think a talk about this should be, is to overview a few of the new, most recent ideas for constructing the citr space. But then you should ask, what about all the old ideas? Are they wrong? I don't think they are per se wrong. And I will just review what is our most recent progress in understanding the existing attempts for constructing the citr space. Okay. So let me start with the general ideas. So the reason is non-trivial to study the question of the citr space in string theory is that the citr space is something we think we observe at the very largest length scales. String theory is a theory about the very smallest length scales. So it's a non-obvious question for any physicist who is not working in our field, okay? This is an extreme example of a lack of decoupling, the fact that I'm even discussing this topic. And the reason is, of course, something that you all know very well, which is a cosmological constant problem, which nonetheless is a very hard problem to explain. And I think many of us are, including me, are sometimes confused about its very definition. So the picture I like to keep in mind is this, is a picture of RG flows. The cosmological constant problem is telling us that if we flow from the ultraviolet to the infrared, then where we end up in the infrared is extremely sensitive to the details of the ultraviolet. Okay, that is really the definition of the cosmological constant problem. And so when we say that the cosmological constant is typically of the order of the cutoff scale, it means this, that tiny changes here, by changes it can mean an extra particle that you add above a certain cutoff. It will make your flow diverge and you end up having, say, Planckian values, negative or positive for vacuum energy, okay? But that's what we observe today is essentially 0, but not quite 0. So how then do we discuss, so the problem at the technical level, as you all know, is that loop diagrams diverge, you introduce a cutoff, and the fact that you introduce a cutoff makes the natural estimated value of the cosmological constant to be the scale of new physics. So how does the string theories go about and do this? We don't compute loop diagrams in field theory, okay? Instead, the way we go about is by using directly the UV degrees of freedom. Okay, strings, well, we should, but we typically don't. So what we are using for sure are extra dimensions, branes, and fluxes. And this I will explain a bit before I go to the swampland program. Okay, so the most conservative way to construct for the citr, which is not the most general way, is to say, okay, 6 dimensions are compact. And once you say this, you get 2 length scales in your problem. The 4-dimensional metric has a length scale, which should be the Hubble scale, which is the largest length scale we know in physics. There's nothing larger than the Hubble scale. And the extra dimensions, they have a length scale, which we typically call the Kaluza-Klein scale, which we haven't observed yet. So it's by definition the smallest length scale in physics we know of, or we think we know of. So the moment you write this, you start immediately with the cosmological problem. You have a huge hierarchy by just even writing this formula and interpreting it that way, okay? Good. So I wanted to say this. And so what we do is we write down this formula and we try to solve the string theory equations of motion. Of course, we cannot, okay? String theory is not sufficiently developed to just attack this. So what we do, and this is crucial for the rest of my talk, we go to what I call the boundary of string moduli space. And at this boundary, we think we can do computations. What is this boundary, roughly speaking? It's to go to parametric small string coupling. So we can ignore string loops or we can keep a few of them. The same with field gradients like curvatures, okay? We expect them to be small in string units. When they're small in string units, we can use 10-dimensional supergravity plus leading corrections. Okay. This framework I call the boundary of string moduli space. Note that the 2 control parameters here, they are actually fields in 4 dimensions, and you should stabilize them. So whether or not this is the right framework depends on how you stabilize the fields, and that's the difficulty of this program. Okay, remember that the volume is a field, and whether or not the volume of the extra dimensions is small will make sure that this is okay or not, but also the string coupling is a field. And note that both of these fields determine the Planck scale in 4 dimensions through this formula, okay? Good. So once I'm in this boundary of string moduli space, which I depict here, so here you see the inverse string coupling, this is weak coupling, here you see the volume in string units. I would say we're in this corner. That's where we try to find something, no? In this corner is what I just said. What we do is 10-dimensional supergravity with leading corrections. I didn't write the leading corrections. I wrote log means localized D branes or the antifolds, NS5 branes, whatever. Okay. And then the game we play is we say, look, the vacuum energy now is the energy in the fluxes, in the branes, and in the curvature. And what we try to do is we try to find solutions that minimize the energy. And then we have to, apologies, then we have to arrange them such that they are here. And when they're there, we can trust the calculation. This is the game we play. And then the hope, for sure, what we have seen, we have, you know, a landscape of this, ADS, but the question is, do we have a landscape of the citr? That's the question at stake, and that's the framework. And the reason this is okay, because this is discussion I like to have on a conference. When you do this, are you computing 3-level vacuum energy, or is this the really renormalized value? It's the second, okay? That's the beauty of working in string theory. It's not effective field theory. All the corrections to this result should be small. Although we know we should talk of loops, of the fields that are present, whatever they are, no matter how complicated they are, the full answer up to small corrections should be this. And that's the advantage over a field theorist doing the same kind of computations. And to me, that's a crucial point. Okay, so why do we do all of this? Well, I think there's nothing else we can do, but maybe I want to point out an important feature of one of the ingredients in the game, which are these guys, the fluxes. So what was already pointed out a long time ago by Dinah and Cyborg, and I think other people, is that Forget string theory, it's more like a general field theory statement. Usually when corrections to a potential are important, they are important at strong coupling. But it's the corrections that can stabilize you. Okay, that's roughly speaking the Dine-Seiberg problem. So Dine-Seiberg argued, oh, vacua tend to live at strong coupling. Vacua tend to be here where you have no control. So you cannot compute it. What do fluxes do for us? They are supposed, this is why they were invented, they should give us a way to go outside of Dine-Seiberg. Fluxes are a 3-level ingredient, which we can hopefully tune enough so that we can get vacua in this part of the potential where the coupling becomes small. Sorry, I might have inverted small and strong, but I think you get the point, no? So the aim of the Flux Compactification program is to construct vacua which are calculable. And one should never forget about this fact. So the solutions should be under control. So the question is, do fluxes indeed do that? Can we stabilize at the bounded moduli space? For ADS, the answer is yes. There is no doubt. Can we do it for the citr? Well, I think it is fair to say that at this point, a majority in our field would agree with the following statement, that for the citr, no. We cannot find the citr here, at least parametrically, okay? And the reason you cannot is, think of the way you get ADS vacua under control. There tends to be a number which you send to infinity, say the number of colors for ADS5 plus S5. When you send them to infinity, you get parametric control. What we found out, I think, in the last years with more certainty is that there will never be a number like that for the citr space, okay? This has been, for instance, shown in certain concrete setups by these people here. And this is at the essence of the swampland arguments against the citr space. Yeah? I hope this message is clear, because if there is one message of my talk I want you to remember, it's this. Okay, so if you're not so interested in the rest, on all the details, you can do something else, but this was the main message I wanted to convey. Okay. I also want to point out how non-trivial this is. Okay, many people say, if you can exclude it in the parametric regime, you have proven nothing. Okay, well, I disagree. The whole point of dualities is that weak coupling corresponds to strong coupling in other string theories, okay? So what we exclude in string moduli space is rather non-trivial corners, all right? Okay, there is some 3-year-old attempt, which is extremely superficial, to classify all existing de Sitter constructions. It's superficial because we wanted to be pedagogical. After that, there appeared a review, which I think was nice in the sense they took a complementary take. This review was a bit negative on how to get the Sitter space. They were much more positive. And they also discussed the important case of quintessence, something I will not discuss. Okay. So forget this issue of strong and weak coupling. What were the reasons before the landscape people were saying the Sitter space is hard, but maybe not impossible? The usual arguments you hear is because you break supersymmetry. Because of the many fields, there are statistical arguments in random supergravity that you typically do not get a stable vacuum or metastable. And that's a problem because anti-de Sitter space can have tachyons if they're above the BF bound, but the Sitter cannot. Okay, so the statistics is more complicated for the Sitter. You can ask yourself, these statements are of course correct, but are they enough to explain all difficulties? I would say for sure not. The moment you work on this topic, you see things going wrong for very bizarre reasons, as if there is a conspiracy, okay? And I'm one of those conspiracy thinkers, or, well, I'm not saying I want to say this is true, but I think it should be an acceptable line of thought to think that string theory contains no de Sitter vacua at all, right? And I'm not advocating this now, okay? But I also want to point out, so some people think this is a crazy thought, but I want to say this is not true. And there is a parallel workshop going on today, which will start today. And you can ask yourself the same question, does a Sitter space exist in effective field theory? Forget UV degrees of freedom. And we have heard, I think Polyakov is one of the first to push this program saying no. Okay? And I think this is an even more complicated topic than the string theory constructions. I'm still trying to understand it. And I would maybe, invite you to go to one of the talks of the parallel workshop. All right. Good. So this is the end of the first part. And I would just want to say what is appearing on the archive today, right? I think I've been able to classify it in 4 different pieces. I would say some of us carry on as in the old days, and they just try to find more and more and more. And they sort of ignore the paradigm shift due to the swampland, which I think is okay. If you don't buy it, then this is a normal thing to do. Other people try to find, want to go beyond the technical battles of the last 20 years and try to see patterns, okay? Reasons for the difficulties. And more important, find links with other branches of physics. And in my opinion, that is the essence of the swampland program. It is try to understand the patterns. Why are things happening the way they happen? It's a question which was not sufficiently asked, I think. Others still differ from too and just try to find more the citr vacua, but moving away from the lamppost with completely new ingredients. And some other people say, look, there's been so much work on the citr vacua, let's not just throw it away, let's just keep on working on it and see, go to the details of it. Does it really work? And I would say those papers which I've been involved in are also motivated by the swampland program. The rest of the talk, I will give examples of this first. Then I say very quickly something about this, and then I go into more detail here. Okay, any questions at this point? Okay, so the swampland program. I guess I don't need to explain it anymore. And we all use this really nice picture by Eran Palti, which I should not explain. This is the energy scale. This is a space of theories, UV complete versus not UV complete, okay? But I do want to mention something about the swampland program, why I particularly like it so much, okay? I think it was, and I already emphasized it, it was a highly needed paradigm shift in the field of string phenomenology and string cosmology. So instead of trying to reverse engineer effective field theories, which kind of was the old way, and if one does that, you typically arrive at the almost anything goes picture, we ask another question. We ask, what is not possible? Logically, these are identical questions. If you tell a mathematician, they say you're doing the same thing. But somehow it does something different when you do the calculations, okay? So this is why we rather see inequalities instead of equalities. And let me make it clear, inequalities are a sign of being precise. Equalities are more a sign of being less precise. I hope you understand why I say that. We're breaking supersymmetry. The moment you write inequality, it should always be an approximation, okay? Whereas inequalities are an attempt at really being precise. At least in the sense that you trust the inequality. The keywords of the program, I would say, are interdisciplinary and focusing on the why and trying to find the patterns. The criticism on the swampland, which is totally valid, is that there's a lot of heuristics. But let me be clear, it is not all heuristics. In fact, the attempt behind the swampland program is the very opposite. It's an attempt to really increase the precision in the field. Okay? But the current problem of the swampland program, which I think everybody will admit, is that the trustworthiness of swampland statements are in the opposite directions of the usefulness of them. Okay? And especially the ones about the citr space, let me be clear, they're here. Okay. So let me review some of the things I think we've all seen when it comes to the citr space and the swampland. In this paper in 2018, which was introduced on the strings conference, we saw this quite striking claim that all effective field potentials should be bounded by a positive number like this C. Okay, so this excludes the citr vacua. But then immediately right after it was pointed out, okay, nice, but the Higgs potential is a clear counterexample. Okay. Also, for people like me, when this paper came out, it was like, really? Because we constructed the citr vacua without any weird ingredients. But they were all tachyonic, but there's no tachyon mentioned here, okay? So yeah, that was a bit strange. I must say though, all the classical, the citr solutions, so this is a line of solutions which I think was introduced by Silverstein, is where you try to get solutions really from 10-dimensional supergravity without leading quantum corrections. If you do that, the precision is much higher. And we constructed them, but nobody found a stable one. But I must say, after the swampland program, we started looking more carefully at our solutions, and we found that all of them are at strong coupling. So forget the tachyons, they're not even solutions, okay? So the classical, the citr vacua are not counterexamples to this. That's very important to keep in mind. Because whenever we found them, they're in a regime where we shouldn't trust the calculation. So we cannot say anything about the potential. But the Higgs is still a clear counterexample. Inspired by these statements, these people went on and they said, look, there should be an extra condition if this is to make sense. And this is a condition essentially saying that, look, you should look at the stability. Maybe the citr critical points are okay if they're tachyons. And that's essentially what this one is saying. At the same time, around the same time, some heuristic derivations of this inequality appeared, and the derivations sort of needed this as well to work, okay? And what I will do, I will present this derivation because it's much easier to explain. So let's see, you can see some real heuristics at work. Okay, so this is as heuristic as it gets in the swampland program. So please don't confuse the program with only these kind of suggestions. Okay, so let's see what Hebecker and Raze did. They say, well, consider some direction in field space and go to the limit, go to the boundary of it. There is a conjecture, which is one of the more precise conjectures, which we tend to believe, which is called the distance conjecture. And the distance conjecture says that if you go to the boundary of moduli space, there should a tower of states appears that corrects your effective field theory. And this tower of states has typically this behavior. The masses go in multiples of this negative exponential. Okay, so the masses go down, and this is why your effective field theory gets corrected. So the number of states below a certain cutoff that you introduced in the beginning must be something like lambda over m, right? On the other hand, older work by Valley, which is called the species bound, implies that really the Planck constant gets renormalized when I have many species, and the cutoff of my field theory should something be like m Planck divided by square root of n. This is an old result. So if I combine the two and I eliminate n, I find that my cutoff depends on the distance in field space by this definition. So you see that also your cutoff is lowered the moment you go further in field space. Okay, so how do we get to the citr now? Well, we just need one more thing. If I have a potential and it has a minimum or some critical point, it relates to the Hubble constant like this. No, this is a well-known formula. But of course, for me to trust it, the Hubble constant should clearly be an energy scale which is below the cutoff scale. So this must be true. If I combine the following things, I get the following inequality for the potential. I see that the potential is bounded by an exponential function that is decreasing. Okay. This is highly heuristic, but I think it's things like this that explain why string theory potentials behave the way they do in the asymptotic regimes. Okay. All examples we know exactly behave like this. Although this derivation was very heuristic. The same derivation, as pointed out by the authors, clearly suggests like a loophole, a way out. Just think of some function that is decreasing but has oscillations in it. Then you can be trapped in a local metastable minimum. Okay. This was about the parametric regime, where I said there is no single example of string theory where there is a de Sitter. What about away from the parametric regime? So there is this confusion that the swampland community says there is no de Sitter. That is not true. The swampland community, at least, especially Umrov-Vafa, has suggested, look, maybe they live at strong coupling. And then there has been an argument, but okay, it still should be very constrained. And what is the constraint? Which is a constraint which has very loose motivation. I have to be honest, this is the most heuristic part probably of everything. It's called the TCC conjecture, the Trans-Planckian censorship conjecture. And the suggestion is the following. Maybe what string theory forbids is that sub-Planckian fluctuations can freeze out. Sorry, that's not correct. They should not become super Hubble. That's the most precise statement to make, okay? And I think if you want to say, personally for me, the motivation is a bit like ordinary censorship, okay? Ordinary censorship means that you cannot see the singularity of, say, some object like a black hole, because otherwise if you could see it, you would go there and you see the full UV degrees of freedom. Somehow physics always forbids this. It's the same with cosmology. If things expand, but you could actually see sub-Planckian fluctuations, it's the same as seeing a singularity, okay? So it's not that crazy to have ideas like this. And we have seen connections like between the weak gravity conjecture, which is very firm, and cosmic censorship, okay? So it's not a crazy thought at all. So the moment you assume this, so this is my final scale factor, this is my initial one, so this is a stretching of a fluctuation, and it should always be sub-Hubble. Okay, that's what the equation is, and this is the integrated equation. So what people did is they analyzed this constraint in terms of the boundary of field space. And indeed, they find something like the original de Sitter conjecture. They find that, you know, this has to be true, and they can pinpoint this number. So that's nice. But what about inside string moduli space, where things are strongly coupled? The only thing this equation then gives you is a bound on the edge of a de Sitter universe. And this bound means that it's sort of short-lived, but it's perfectly consistent, for instance, with our own universe. Okay. I'm almost done with introducing the swampland. I just want to mention one more. This is where I want to advocate, of course, my own work. There are other swampland ideas which have to do with the citr space, but they don't necessarily constrain the existence of the space. They rather provide consistency conditions on it by giving constraints on the matter content living in the vacuum. Okay, so the fluctuations in the vacuum. One famous one is the weak gravity conjecture, or the electric version of it, which, as you all know, says that a theory has to at least contain a single particle. When there is a U1 gauge field, there has to be a single particle at least, or some state which obeys this equation. A state which would be super extremal if it would be a black hole. Okay. This is an example of a swampland conjecture, which I think is essentially proven now, but it's not so useful to an effective field theories because it's very easy to make it always true without changing your effective field theory. And where does this come from? You essentially want black holes to decay in an okay manner, okay? In a citr space, following the same logic, you get, again, this equation, up to tiny corrections, which they are not important, which are Hubble suppressed, okay? But there is one extra condition, which I will explain is the work with it, which is that the theory has a constraint for all charged particles. Okay, particles cannot be arbitrarily light if they are charged. They should always be heavier than this combination. This is a charge, this is the coupling of the U1 field, Planck mass and Hubble constant. Okay, so if this is correct, it's an extremely non-trivial UV-IR connection. And the moment you have a non-trivial UV-IR connection, that's when the swampland gets very constraining and useful to an effective field theorist as well. Where does this come from? And then I go to the citr constructions. Oh, my axes are gone for some reason I don't understand on this picture. Okay, but there is an axis here which is charge of black holes, and this is mass. Okay, in flat space, all black holes live below this line, so they're everywhere here. In the citr space, it's different. In the citr space, black holes cannot be larger than the Hubble horizon. So in the citr space, the diagram of existing charged black holes, they live in this, what we call shark fin region, okay? That's where they live. So what we have done is you have to enforce that black hole evolution, make sure that the weak gravity conjecture, if you like, in flat space, make sure that black holes, when they're here, they quantum mechanically can evolve and evaporate. But in the citr space, it's non-trivial because you have to enforce that black holes here near this boundary don't go out. Okay, if you ask that, you get this inequality. Note the squiggly line here. There is a non-trivial connection to something which is also rather well established. That's the magnetic weak gravity conjecture. Okay, let me quickly review that. The magnetic weak gravity conjecture essentially says that if I look at the monopoles, now at magnetic particles, the radius is roughly 1 over the cutoff of the theory, and we want that this radius is larger than the corresponding black hole, so that it's really a particle. But it should be smaller than the Narai black holes, which are these guys here. No? So for a small monopole charge, you get a standard magnetic weak gravity conjecture in flat space, but you get an extra inequality now for these ones. And this is something nice. This was observed in this paper, which for reasons we don't understand is completely ignored, but it's a very nice paper. They found that the U1 coupling in the citr space of any field, of any Maxwell field, is bounded from below. Note how this is nicely consistent with my statement that the citr space cannot live in arbitrarily weak coupling. Also not for some U1 field. It's exactly what this is saying. So the same condition you can reproduce from our bound by applying our bound to the weak gravity electric particle. Then you have to combine two inequalities and you get this. No? And if we say, well, this is the fundamental one, we can actually fix the unknown constant in our inequality and it becomes square root of 6. But that's a detail. That's not important. It's my last slide on the swampland. How am I doing on time? Okay, that's quite okay then. Other swampland papers, they start bottom up. What I just showed you about black holes is of course bottom up, but it's a typical game we play. We look at black holes to understand UVIR connections. But you can also just study the citr space in supergravity, okay, and study what are constraints there. And why do you do this? Well, the hope is that the moment you study the citr space in supergravity, they have a chance of getting an embedding in string theory. And the higher the supersymmetries of the Lagrangian, the more chances you get at embedding them. But the only stable, the citr vacua or metastable ones in 4 dimensions implies that n has to be equal or smaller than 2. There is one counterexample in higher dimensions by Adolfo. He has to correct me, which I think has 4. This says n equal 4, half maximum supergravity, which is not by you, but your friends. This is why I think it's from you. Yeah. Okay. So let's see what is possible in n equal 2. And what was very intriguing is a recent paper by these people. They've shown that all known de Sitter solutions in n equal 2, they're either perturbatively unstable or they violate the Fessina-Lente bound or the magnetic weak gravity bound. And that means essentially that the cutoff is below the Hubble scale. And that makes sense because of those that we know uplift to string theory, they uplift to non-compactifications, as shown in this paper. And non-compactifications, of course, mean that the cutoff of the theory is essentially 0, because there's no gap in the spectrum. So that really kind of makes sense, okay. There have been many more recent papers on the topic of, say, supergravity and the swampland, and I invite you to look at them. Oh, I still have more slides about, okay, this is really the last slide of the swampland, on the swampland, okay? So naively, the existing constructions like kklt and large volume scenario, they violate this TCC conjecture. But that's not entirely true because you can always choose parameters in the theory such that they still obey them. And the reason that is true, but somehow I haven't seen this pointed out in literature, is that the age of, say, a universe a la kklt is not the one given in the kklt paper. There is a dominant decay channel, which was pointed out in these papers, which is the brain flux decay channel, means that the decay is much faster. And I will talk about that later. What we found in a recent paper, much to our surprise, we were analyzing all these weak gravity, these swampland bounds for kklt, but not TCC, but the ones we are getting more certain about, say, weak gravity or even this Festina-Lente bound. What we found to our surprise is that these bounds exactly rewrite themselves into inequalities that you can find in the original papers on kklt, which was really in a way nice. The consistency conditions they wanted are the consistency conditions you exactly get from these swampland bounds. So you think this is a very strong argument in favor of these constructions. But of course, it's not entirely correct, because what we found is that the swampland bounds are consistent with local stability constraints. So here is a kklt picture, this is a Calabi-Yau, this is a warp throat, and at the bottom of the throat there is a SUSY breaking anti-D3 break, okay? The stability of this thing or this thing, the throats, they translate into the swampland bounds. But if you trust also the same papers that construct the citr vacuum, they say, look, if I break SUSY here, nothing will happen here in the bulk. It's an important assumption. If that is true, we can violate the weak gravity bounds. Why? We put these 7 branes here with the right properties such that there is chiral matter, and I have massless fermions. And massless charged fermions, they violate all these conjectures. Okay? So my interpretation of this, I will stop now, is that there is, if the vacua exists, it is not true that you can decouple the SUSY breaking from the bulk. And I will end my talk with an explicit recent paper showing this. And if I understand now, there is a small break.
Yeah, so we are going to stop for a few minutes because the mayor. Yeah. The mayor of Corfu will say a few words, and then we will go on with Thomas' talk.
So we are very happy to have the mayor of Central Corfu with us. She didn't want to interrupt, but I didn't realize myself that we were not pieces of half an hour, but a whole hour. And being so busy, we had to interrupt. I had at the meantime the opportunity to describe what we are doing here about the past workshops and things like that, what is going on, that will be something in parallel in the garden. And she was quite impressed actually from the organization of all that. And the most important is that we can see all the progress with buildings, which when they finish will go all to a new phase. When you come here, you will have offices. You will be able to produce locally research, and that's a great thing. Thank you very much. So, please.
Sorry for the interruption, but it's a great pleasure for me to welcome you all here in our beautiful city and island. As you know, Corfu is a multinational and multicultural place. Through ages, all the center of powers were occupied Corfu, British, French, Russian, Venetians, and you can see all around the old city especially, their footprints in the building, in the architecture, in the gastronomy, in our culture, in our music. So through ages, it was a multicultural place and a historical place. This fact was recognized in 2007 when Corfu was recognized as a monument of UNESCO and is protected by the International Catalogue of UNESCO. So this is a very important matter, a very crucial matter for us and for the promotion of our island and our city. And with the help of Professor Zoupanos here, he helped a lot municipality,
With the help
of all of you, of course. We are trying, and we are in the last step, I think, to renovate all the buildings around here. I think next year they will be ready. So with you, we can produce great things, of course. And here in Paleopolis, Paleopolis are mentioned in Corfu too, in the Iliad of Homer. It was the kingdom of King Alkinos. And I hope in a few days you will stay here, you have the chance to look around and to see our great monuments, our great history, the palace, the two fortresses, the old and the new fortress, and the old city, the historical city of Corfu. And I think it's a great experience for you too. So I don't want to interrupt anymore. I hope good luck in the scientific goals of your conferences and a pleasant stay in our city.
Tonight we have a reception in case you have time.
Thank you very much for the invitation.
Thank you very much.
Great luck to all of you.
So back to the citr space after these nice words by the mayor. And I realize I still have 20 minutes. It might be a little bit too little. So I think I should skip one of the elements in my talk. So here I wanted to discuss the novel ideas. I think I will skip it, although I think they're super interesting. So let me just mention them. And I think if I skip them, well, just only mention them, we will have time for the last bit. There was a paper by the group in Uppsala, which does brain walls in an entirely new fashion. I really invite you to look at it. I think it's quite striking. There was a paper by the group by Cordova, De Luca, Tomasiello, who found classical de Sitter solutions at recoupling. So that's in immediate contradiction with what I said before. There was an interesting, very interesting reply by these gentlemen pointing out why they think the solution fails. I invite you to look at it. I mean, if there will be proceedings, I think there might be, then I will explain all of this there. And then, for instance, recently also, I think a really nice attempt by these people where they say, look, I mean, that's my way of saying it. Lots of the problems we have come from instabilities associated to orientifalls. Let's do away with them. Let's break SUSY at the KK scale with hyperbolic spaces. And the new ingredient that replaces orientifalls are Casimir energies. Okay. And okay, I think it's very interesting. Let me just mention that all of these three papers, and there are many more, they are really novel ideas. I think they're super interesting. We should study them. Nonetheless, all of them have their possible issues. Okay, so that's typical to the Sitter space in string theory. It just never works immediately. Now the question is, how big are these issues? And I think we should know in a few years. Then there are lots of papers. I try to put few of the, well, I will try to make a full classification of the papers that appeared, but I will not have time to mention them. Okay. So let me go to the last part of the talk, which is a big part. I mean, we did all that work of the last 20 years, so you cannot just throw it away and look at other constructions. It is important to really make sure we finish those debates, okay? So I will do this. And I'm afraid I will have to speak again about kklt and anti-brain uplifting. You might be tired at this point. I hope not, okay? But I think it's good that we go in so much depth about this. And we should keep on doing it until we agree with each other, right? And it's amazing, the deeper you dig, the more interesting stuff you actually find on the way. So it's not a boring topic, it's a real fun topic. So I'm assuming you roughly know what is kklt. I'm not gonna review it. I'm just gonna mention a few things necessary. So kklt and relatedly large volume, but in a different way. They claim to achieve full modularized stabilization. And for kklt, that's in a SUSY ADS vacua. And the SUSY ADS vacua comes from correcting no-scale supergravity vacua, which are Minkowski. And they're non-SUSY, but because of the quantum correction, you get an enhancement of supersymmetry, and you're back at n equal 1 supersymmetry, and you have some kind of a ADS vacuum where the classical superpotential, that's W naught, is sort of balancing the non-perturbative quantum part. Okay, I'm doing the case of a single Kähler modulus T, and the real part corresponds to the volume of the Calabi-Yau. The point of the kklt paper was this, but then they added something nice to get the citr. They say, look, if such a Calabi-Yau supports a ward throat, we can throw in a SUSY breaking ingredient. It falls down the throat because it's attracted to it dynamically. The SUSY breaking will be redshifted, so it's under control, and you can calculate the vacuum energy, and it can become positive. Okay, and it really relies on a very important paper written before the kklt paper, this one. Okay, that's the groundwork of it, of the last step. Of course, kklt has been claimed not to work by others since its very invention. I think the history of this thing is that people are continuously disagreeing with each other. And some criticism has been refuted with very good arguments. And I will review some results and worries on exactly this SUSY breaking part of the kklt construction. But it's crucial to mention that even the ADS part is under debate. Okay, but that's a higher level of concern, so to speak. And I think we heard about this on this conference, okay? And one of the things is that you need to make sure you can do the fine tuning. I mean, if you balance a classical effect against a quantum effect, you really need to make sure you can tune this to be small. And what you heard at the strings conference mainly was all about this, the important breakthroughs in getting this number to be small. But this is not about de Sitter, that's about anti-de Sitter. So the way I think about the worries of the Sitter space, kklt construction, have to do with the two ways the vacuum can decay, in case you would believe the construction. So here is a kklt potential from the paper. This is the ADS, this is the uplifted part. There you see you can decay from here to there. That's a non-perturbative decay in case you trust the calculation. And this corresponds to a decompactification. And that decay is only there, of course, at finite volume. What I'm trying to say here, this is something that only exists in a compactification, okay? However, you can study anti-brane stability outside of a compactification context to get more control. So these are models where the gravity decouples. These are holographic models. And then, but of course, I mean, you can also do that here, no? But to get, if you want to really zoom in on the throat, you can just isolate the throat and ask yourself, is the anti-brane stable in this throat or metastable? And to then make your life simple, you go to non-compact models where gravity decouples. And then you can study this stability channel, the decay from de Sitter to anti-de Sitter. But of course, if gravity decouples, it's from Minkowski to Minkowski, but okay. So let me start with this. And then I have to review very quickly this work of Katchel, Pearson, and Verlinde, which was in the Klabanov-Strasser throat. So in a non-compact model, and they say, look, if you put, if anti-D3s, anti-D3 branes are at the bottom of the throat, they actually can decay. And they found out how. Okay, that's what this paper is about. What they realized is that the Myers effect changes these anti-branes into an NS5 brane. And so what is this blob here? This is the A cycle. So this is the Calabi-Yau. This is the Klabanov-Strasser throat. And the 2 cycle pinches off. And at the bottom, there is only the 3 cycle. And this is where you put the anti-branes. Okay. Myers effect makes that it becomes an NS5 brane. And if this NS5 brane goes to the other side, it costs energy to do that. It's like an elastic band, you need to, increase it. But if it can do that, it corresponds suddenly to D3 branes, to M minus P D3 branes. And the way you interpret this, what had happened is that some of the 3-form fluxes materialized in D3 branes, in MD3 branes. And that can only be possible if some of the fluxes drop 1 unit. And of course, the NS flux dropped 1 unit as the NS5 brane moves over. Okay. So we interpret this as a nucleation of MD3 branes, but those MD3 branes, they see the P anti-branes and they decide to annihilate. And this is how you go to the supersymmetric vacuum. This is a supersymmetric vacuum. Okay. And this is supposed to be holographic dual to dynamical SUSY breaking in the Klebanov-Strasser gauge theory. So that was the importance of the paper at the time. We want to understand dynamical SUSY breaking in holography. The calculations they did were very nice. They found that metastability is guaranteed if P over M is small. P is the number of antibranes, so if the flux is large enough. Nicely, this also corresponds to the limit in which the back reaction is supposed to be small, so you can trust the calculation. So that's kind of nice. So to summarize what they found, using probe calculations, is that when P over M is small enough, you have a metastable state. When it's too big, you have a direct decay. But then people started worrying about back reaction corrections. What does that mean? I'm going to make it very simple. Say, okay, the green is a background flux, okay? And the red is the anti-brane. And I told you, this green stuff can materialize into D3 branes. These D3 branes annihilate the anti-brane. But if back reaction makes that the flux becomes very large near the anti-brane, because it attracts it, then you could think, oh, this decay channel will become immediate. And after a series of papers from the Saclay group, indeed, they said, look, this flux is actually diverging in the supergravity limit. And if that is true, we argued, even if you cut it off at string scale, it will cause direct brane flux decay. And that was an issue. And let me be very quick then. I think this issue was resolved in the following way. We started to at least write down what would be the full back-reacted solution. You cannot solve it, of course, but you can at least write down an ansatz that could cover it, which is completely general. I mean, you just see it, arbitrarily 6-dimensional geometry. Let me not go to the details. The thing you need to know is that C4 alpha is a scalar. So it's a 6-dimensional scalar, if you like. And this is the C4 gauge potential to which the brane couples. And then you can show with these general ansatz that the three forms have to fulfill this relation. This is F3, this is H3, and this is any other three form you need to add to make it work. Then you can show, and this is trivial, that this ansatz implies this relation for the flux. And now you can ask yourself, when is this blowing up? The amazing thing is that you can argue in general ways when this will blow up. You can show that the moment this number is non-zero, this is blowing up. Let me quickly explain what this is F here. F would be in case I add temperature. There's a reason why I would add temperature to the branes. I will mention it later. Okay, the bottom line is you can show that if this is not zero, the thing blows up, right? There was a paper saying no, at finite temperature, it can still be finite. Okay, because of some magic cancellation between these things. We'll come back to that. So you should ask yourself, can I take it to zero? Oh, I probably need to use a supercomputer and start calculating. That is not true. The nice thing is you can do a fully back-reacted calculation, which is called finding the smart relation for this setup. And this smart relation, just like black holes, says something about the asymptotic region versus a near brane region. And it's a fully back-reacted result. And here is a smart relation. So this is the ADM energy. Okay, this is not important. This is the gauge potential near the brane. This is the 3 brane charge. This is the gauge potential of the NS field near the brane, and this is a 5 brane charge. Okay. So here they are defined. This is not important. Forget what this is. I think you understood it roughly. So what do you see from these ansatz? SUSY breaking means that this needs to be positive. You see that it's, if you take this to be zero, and you say there is no polarization, because you don't put it in the ansatz, then you never can break supersymmetry. This is the same as spitting out a singularity. Okay. So only when you allow in the ansatz the NS5 to polarize, you can take this consistently to be zero and there's no singularity. All right. A similar story holds at finite temperature, but okay, we'll So these calculations, we have seen two pieces of evidence. There is a probe calculation by KPV, which is calculated in a regime where you should not do it, but people took it as evidence. And then there's a back-directed calculation showing at least the singularity can be absent. I think the real breakthrough came from people like Niels and the program they had set up, which is a black fold formalism, which allows you to do computations somewhere away from these two regimes. Okay. And what was amazing by using the black fold formalism, we can study Katz-Pearson-Verlinde setup even at finite temperature. And what did we get? We got this. This is the potential we got. I must say, if you go to 0 temperature, you exactly get the KPV potential. So that was amazing. At 0 temperature, we exactly found the potential written in an approximation which was not valid. To me, is a big surprise. We also got something at finite temperature. And this is just a side remark. This is this thing that Kevin Hartnett talked about, but let me ignore that. What you see, the point is that there is a metastable solution. There's a black NS fibrate. Yes. And what is nice is that if you add too much temperature, and I didn't draw it, the potential goes like this. You lose it. You lose a metastable state. And what is very nice is that there's a geometrical picture. Here is the NS5. And when you heat it up, it develops, a horizon around it, as you know. And if you heat it up too much, the finite temperature horizon eats up the topology and you don't see it anymore. And at that point, where it becomes a donut, it's exactly the point where you lose a metastable state. So this is very much evidence in favor of metastability because it behaves like a gap state. It can withstand a certain amount of temperature, and above that temperature, it decays. So I would say this is all very much in favor of the metastability. However, I have to be honest, there has still been an interesting line of work by the people in Saclay, still pointing out non-trivial instabilities, and I invite you to look at it. Okay, the final bit is the honor decay channel. What about this one? And this is something that only exists at finite volume. What happened there? I think if I can get to this slide, I'm happy enough. Okay, so there has been a series of papers which started by the people in Hamburg, and the problem was the following. They said, look, modularized stabilization comes from the D7 stack in the ultraviolet, and here is a SUSY breaking. What you kind of want is that the two decouple sufficiently much, because then you can just add the SUSY breaking, and you can, this is your potential. It's a ADS plus the SUSY breaking. But if there is some non-trivial communication, there is corrections to this. And the usual story is, no, this is a warped throat, so this is sufficiently warped down. However, any back of the envelope calculation says that that might not be correct. And here is the back of, the simple calculation. You can either say things don't redshift enough when they go out of the throat, but I think there have been enough calculations showing that probably they are. But what about blue shifts? Can there be a non-trivial communication from the D7 stack to the anti-D3 brane? And this was estimated in this paper by just looking at dimensional analysis. You see that the gaugino condensate should undergo a blue shift of this kind. If you put this in the kklt potential, you see that this has to be of the order of the number of anti-branes, so it's order 1. So that naively suggests that this term is as big as the other terms. And then you lose control. So I'm not going to explain what happened in this case, so I know I don't have time. Let me just summarize what happened there. There have been lots of papers. Some of them were discussed at strings, and here is my highly biased opinion on all of this. I think there has been impressive progress on the 10D description of the gaugino condensates, okay, which is really nice. And the 10D singular behavior, on top of what I mentioned, there was a singularity again, okay. Also, that is now understood. Also, that singularity is gone. But the confusion about it uplifting or not has nothing to do, in my opinion, with all of the things that have been developed. So it was about the definition of the semi-classical limit, in which some papers, including mine, differ with others. The blue shift issue has not really been studied. It has not even been computed. So I think for me, it's still on the table. If you combine it with what I said before, this Fessina-Lente argument, it shows that it could be a problem. So if I have 1 more minute, I want to explain that. So there was very interesting work, which I think is, which I'm going to skip. And then it brings me to the very last slide, which is a singular bulk problem by these people. And then I'm done. What I'm going to tell you now is a recent paper that exactly shows what I just said, okay? So what happened before? So in those papers, these are, 2019, 2008, people already noticed a problem with kklt. If you check the numbers for it to work, you find that the size of the throat for it to work is bigger than the whole Calabi-Yau size. So that's naively a problem. But that was very imprecise statement. What Hebecker did was the following. They really went to study it. They said, this cannot be a correct statement. They say, take for instance GKP, forget kklt, don't stabilize the killer modulus. Then you can already see the killer modulus is a modulus. I can, with a warp throat, choose any volume of the Calabi-Yau and it's a consistent background. Okay, so they realized it has to be more complicated. So they went on and they calculated. And what did they find? And I'm going to keep it with this. There's a one-slide explanation of this calculation, which, but I'm not going to give it because of a lack of time. They found this. So this is the internal Calabi-Yau. These are the 7 brains. And instead of the solution going singular, a few string lengths away from a 7 brain, what you expect, they found that the bulk of the Calabi-Yau becomes singular the moment you demand the numbers in the game to be such that anti-brain uplifting becomes possible. That is crucial. This is not against kklt ADS, it's specifically about the citr. You tune the numbers such that the uplift is possible, you get this. Okay? So think about what I just said before. This is a clear sign of a lack of decoupling between bulk and throat. Here is the one slide where you can see it. I'm not going to give it. I'm going to the summary. Here is my summary, which are frequently asked questions I get on a conference. So are there the citr vacuum and string theory? I would say we're still arguing. The answer is either none or a huge landscape. Is there anything you people can agree on? I would say yes. I would say 90% of the people agree there are no de Sitter solutions in the parametric controllable regimes. So has there been any progress whatsoever? I would say yes. We have learned an immense deal about SUSY breaking in string theory, and I think we actually agree on more things than ever before. Will you settle anytime soon this discussion? I don't think so. Thank you very much.
Well, thank you, Thomas, for the very nice talk. Are there any questions in the auditorium? No questions at all? I'm going to check the online participants. No, not there. Well, then maybe I will ask, there is one. Ah, Luca Martucci. Okay. Luca, you may go ahead.
Hey, hello. Hi, Thomas. Thanks a lot for the nice talk. So I have a question about quantum correction. So you said in the first part of your talk that basically in string theory, you can in some sense neglect the quantum corrections, which in a four-dimensional effective field theory approach would be actually the origin of the hierarchy problem, the cosmological constant problem. So can you elaborate on that? Because that is not completely clear to me. I mean, we want not only to get a solution which has
something in the boundary of C moduli space. What you compute is a full result up to small corrections. If you set up a field theory calculation, that is non-obvious because you have all the fields. What I'm trying to argue is that if you reformulate this infinite asymptotic series in field theory, they should regroup themselves into string perturbation theory asymptotic series. Okay, and that's highly non-trivial.
No, I understand. I understand your point. Can I conclude just a moment? Because we also want not only to find a solution which has some four-dimensional de Sitter geometry, but to find actually a four-dimensional effective field theory describing a non-supersymmetric four-dimensional effective field theory describing our world. No? So, I mean, this fine-tuning that you were talking about at the beginning of your talk, I mean, should be automatically somehow implemented
May you speak up a bit?
Okay, sorry. Can you hear me? No, you cannot.
Yeah, if you speak louder, it would be better.
Okay, yes, it was about, I mean, the fact that you don't only want the solution with this citr four-dimensional space, incorporating the citr four-dimensional space, but also a full non-supersymmetric four-dimensional effective field theory. So that fine-tuning that you discussed at the beginning of your talk should be automatically, I mean, from a purely four-dimensional effective field theory viewpoint, should be automatically implemented. So I just wanted to ask you, I mean, if you can elaborate on this point.
I'm not entirely sure I understood the question, but I'm going to make an attempt. So I think what you're asking is the real problem in the CC problem in field theory is that when I have a non-trivial matter content, because I want more than pure de Sitter, right? If I have a non-trivial matter content, I have the standard model, for instance, there is a radiative instability problem, okay?
Yes.
You're asking, how do you see that in string theory? I would say we see it in a very nice way as I illustrated here. So imagine I want to engineer the standard model and I put some standard model branes. I don't know whether these are D3 branes or whether these are D7 branes somewhere else. You see it also in string theory. So the moment you have to add something extra, you have to redo your modularized stabilization. You just see that everything reshuffles. And in particular, with what we're learning now from these warp throat examples, we see that there's no way, especially with the last paper by, say, Hebecker, and you know the resolution proposed by Carta et al., you still see that if you would put somewhere standard model branes, they will be heavily affected by the SUSY breaking. Okay, so there is no decoupling, and I think you would have to redo the calculation of the vacuum energy. So I think that's sort of a smoking gun, how you see the radiative instability in a field theory language. I mean, this is a guess, okay, but this is how I would think about it.
Okay, thank you.
Okay, there is a question, Dieter.
Thank you very much for this very nice talk. Since we were, you were also mentioning SUSY breaking, you just mentioned it again. My first question is, do you think that after we solve SUSY breaking, we also have solved the de Sitter problem, or do you think these are still two unrelated problems? I think my personal opinion is that the later is true. They are of course related, but I think one does not solve the other. In particular, as we know, the SUSY breaking scale has to be higher than the TV scale. We know this from experiment. On the other hand, the cosmological constant is much below this scale. It's very, very tiny. And after maybe we have understood SUSY breaking, which is still a very hard, in my opinion, not well understood problem. We can also debate about this. Then we still have to face about, we have to deal with all these radiative corrections in a non-supersymmetric vacuum, in string theory and in field theory, which always generically will lift the cosmological constant from its measured value up to the scale where SUSY is broken. So my first question is, do you think that these are one solution implies the other, or do you think we still have to work much harder and much further?
So from the things I have explained, it's clear that this was cosmological supersymmetry breaking, which is at a completely wrong scale. I fully agree. So I have nothing to say about this, just that my bar is lower. I just try to see whether the cosmology works. The only thing I can add is perhaps that there were a few papers on the archive which suggest that any resolution to the CC problem affects the radiative instability of the Higgs, so that the two are in fact related. For instance, I mean, there's more than one paper. There was a paper by, I think, I forgot the names, Keith Deans, I think, who studied non-supersymmetric strings, and they really see the relation between the two, which is, I think, highly interesting. So it could be, maybe this suggests that the right way to go is not just standard critical string theory. If you want to do cosmology and particle physics together, you have to break SUSY at a very high scale and try to get control over the models.
Yeah, I agree. I think often these two problems are presented in a kind of unrelated way.
Yes.
You have, so to say, two blocks. Here's cosmology, there's another block, which is particle physics. But at the end of the day, and this makes the problem harder, at least this is what I think, one has to solve both problems in one stroke. I think, in my opinion, you cannot really decouple them, but of course I might be wrong.
No, I think the swampland inequalities, for as how much you are willing to believe them, are exactly indicating this. Absolutely, yeah.
UVI mixing presumably plays a very important role in this.
Absolutely, yeah. Yeah.
Okay, we have a last question by Eran.
Hello, can you hear me? Can you hear me? Or
I
cannot
think
hear me? Can you hear me?
we can hardly hear you.
You can hardly hear me. So
There is a problem here, Eran. So if you talk loud, I think we can.
okay, can you hear me now? Or no?
Yes.
A little bit. I wanted to ask you about, so if you have a black hole solution in string theory, then we have some understanding the black hole entropy corresponds to many microstates. Then if we have a de Sitter solution in string theory, shouldn't the de Sitter entropy correspond to many microstates in the microscopic theory? And if so, how are these microstates manifesting within, let's say, something like kklt?
Yeah, I think I understood the question. I would say, yeah, what you're asking is spot on. So I don't really, I mean, I would see, I think it's more a statement instead of a question, right? So if we have a microscopic solution to the citr solution to string theory, it should give us a clue about the entropy counting. But I don't think any of that is available. And for instance, but I think this was sort of the thoughts in your paper who derived, I mean, I presented a simple derivation of this swampland bound. The more non-trivial one, of course, is what you tried, is involves actually the entropy. But so, Eran, I mean, I can only sympathize with this point, but I have nothing really to add on this.
Yeah, I mean, it's just a comment that, you know, if you have a black hole solution, then an effective theory black hole is really many, many solutions in string theory. And those are the microstates of the black hole. So I would expect that an effective kklt vacuum to actually correspond to a huge number, exponentially large in the cosmological constant, of different solutions in the microscopic theory. Just like if you look at like Strominger-Waffer, a black hole solution in effective theory is really many, many different ways to wrap strings around the cycles. But I don't see in kklt many, many different ways to realize a kklt vacuum. So how is this, can this make sense, or that's all I wanted to ask, yeah.
There is no sign of degeneracy in kklt, I would say, at first sight. So absolutely, I can only agree with this,
Okay, thank you. Yeah.
Okay, thank you very much. I think we can thank Thomas once more.
Okay.
So our next speaker is S Arvanitakis. He's going to talk about double space-time from higher algebra.
Thank you. Sorry for the delay just now. And also I'd like to thank the organizers for letting this be my first post-lockdown seminar. Corfu is lovely. Is this how? This works. Okay, so I'm going to start with something we should all hopefully be familiar with. You take string theory, you put it on a flat background, say 26 dimensions, closed bosonic, and out comes a low energy effective theory of the massless modes, the graviton, the B field, and the dilaton, and it looks like Einstein gravity coupled to the B field and the dilaton. So this is a straightforward Einstein plus matter. So this tells us string theory is a theory of quantum gravity. So this doesn't tell us if there's any fundamentally stringy features of quantum gravity as realized in string theory. And this is what my talk is going to be about. So can we find any fundamentally stringy features of this quantum gravity theory? And to do that, I will go to a slightly more complicated background, which is to say not just flat, still flat, but not non-compact and Minkowski everywhere, but it's going to be Minkowski cross a torus. I'm only going to care about the torus bit. Okay, so the effective theory of strings on this kind of background, I'm going to call double fill theory, and I put effective in scare quotes, which I will clarify in a second. And this was really considered in by Chris Hall and Barton Zwiebach in 2009, and they derived this from string field theory. And they did this up to cubic order. Okay, and the characteristic feature of this, so the one that I can mention very briefly in my first slide, is that the fields of the theory, so which is to say the analog of the metric and Kalbromon field, etc. They don't just depend on the coordinates on the Rn and on the coordinates of the original torus, but also on the coordinates of what we would know from T-duality to be the dual torus T tilde. So you start with a theory on a spacetime with a torus Td, and then you actually get a theory on a spacetime with a double torus because of the string winding modes, which I'll review in a second. So the question now is, Jesus Christ, okay. Sorry, I moved too much. Okay, good. Sorry about that. Right, so the question before I was interrupted by the equipment was, does double spacetime survive beyond cubic order? What if we go to the quartic order in this theory? Like, does this still look like that, or is this a mess, or is this something that's so hideous that it's not recognizably a spacetime? And I'm going to detail some progress in this direction in this talk. So the fundamental tool, which I'll try to give the flavor of in this seminar, is homotopy algebras, which is, it's a kind of, higher or homotopy algebraic structure. In this case, this is a structure that generalizes Lie algebras, and its relevance here comes from the fact, that we have this is the algebraic structure underlying string fields. Okay, so this is the field theory whose scattering amplitudes reproduce string scattering amplitudes. Okay, and then there's an algebraic construction in this framework, which is a homotopy transfer construction, and then you give it one theory formulated in the homotopy algebra language, and out comes another theory. So the question is, can we use this to make any progress with this problem? And I will detail the progress here. So the nice thing about this entire machinery is that what you naturally get is manifestly doubled, because the starting point and the the process you use is everything is doubled. You don't have to kill the duals everywhere. And by construction is consistent with gauge invariance, which is the, the first consistency condition you would check. If it's not gauge invariance, it's rubbish. And you expect, of course, to have gauge invariances because the theory is going to contain an Einstein-like subsector of the things which have no winding excitations, right? So it's going to have a gauge symmetry. And this is, you can also interpret this, this homotopy transfer under some conditions, which I will clarify, as an implementation of a proposal by Ashok Sen that produces Wilsonian effective actions in string and superstring field theory. And this was also noticed by these other groups that put their papers out before ours. Right. So there's still some outstanding technical issues. Namely, there's also a dilaton in this theory, which I now will try to outline where this comes from and why we must keep it. Sorry, I said dilaton, I meant tachyon. And it also prefers Euclidean signature for slightly more obscure reasons. And there's also some, when you're doing this, you also need to deal with some subtleties in when you define string fields on the torus, and these are things that apparently people did not consider before, and we have a long section in this paper dealing with this. So if you like lots of minus signs in T-duality, you should read that section. Right, so let's recall, how can I stop it? Sorry, how can I stop this making the interference? Do I need to sit here or? Ah, thank you. Okay, so let's start with closed string theory. As we know, it's a bunch of oscillators. Just in first quantization, this is the thing we teach beginning graduate students. So if you have strings on a flat space, you have two kinds of oscillators, except for the zero mode oscillator, the two of them agree and they give the center of mass momentum. This is due to the closed string periodicity condition. Whereas if you're on a torus, you can have winding, and then this makes the two zero modes bifurcate, and then you get alpha 0 and alpha bar 0. And then the presence of the momentum and winding, or the doubling of the oscillators, means that the states you have naturally live on a double spacetime. Well, you start from a state which has both momentum and winding, and you need to introduce a position conjugate to the momentum. If you take the T-dual theory, you need to introduce a position conjugate to the dual momentum, which is the winding. So if you want to be T-dual in all ways and in all things, you need to take both positions seriously. So clearly, string theory in the torus is living on double spacetime. This is plain as day. So yes, we must take dual positions as seriously as positions. Okay, so to actually see what this implies for string theory as a theory of gravity, we need to introduce interactions. We actually need to look at the field theory picture. The first quantization is, I guess that's about the most of what you can say about the doubling. And the theory whose S matrix gives the string scattering amplitudes that we get with the usual, Riemann surface CFT prescription is known as string field theory. And it depends on, well, a priori, I'm not going to elaborate on that, a choice of on-shell string background, which is a conformal field theory. And the field is some arbitrary string state. Like you take your world sheet and you write down states on it. And the only constraint it obeys is the level matching, which you've probably seen before. And this level matching does allow, doubling. So for the torus CFT, this condition just gives a relation between the levels and the momentum and winding. These are integers. And yes, the closed string field theory in the torus is manifestly doubled, and it actually enjoys T-duality as a symmetry. This is spontaneously broken for most moduli, and if you have very special moduli at the self-dual radius, etc., this is actually a gauge symmetry, as these people show. And right, you also have doubling even for the states of equal levels n equals n bar, and these are the states which contain the graviton, dilaton, etc. kind of states, which will be relevant in a second. So what these people did is truncate to the levels n equals n bar equals 1, which if you have a Minkowski background, they're just a dilaton, a metric, and a B field, the normal ones. Now they're going to be the double geometry versions of these. And this is consistent to cubic order, and this they call this theory double field theory. And at this point, you should be very surprised because, well, consider this as a kind of effective field theory. Well, you can't, because states in this multiplet, states in the states with this, I guess it's hidden by the bar. Well, they're not all massless, or they're not all light compared to the rest of the states in the spectrum. Because if you keep the radius finite, say finite by small, these states will be light, these states will be really, really heavy. Okay? So it's actually very interesting that this is consistent by itself. And moreover, it's not just consistent in the sense of gauge invariance, it's also physical in the sense that you have a kind of, you have a locality in the resulting action. So you have, it turns out you have a pair of fields, you have a generalized dilaton, which is a scalar, and then you have this Eij, which is a non-symmetric thing. You can view this as a perturbation of a doubled or generalized metric, if you've seen such things. And the Lagrangian you get to cubic order from string field theory is vaguely Fierz-Pauli-esque. So it's not very illuminating for my purposes, so I just displayed a couple of terms. But it's something very reasonable, something you would just naturally write down in polynomial, and it manifestly lives in doubled space. And moreover, because, as I said, everything needs to obey the level of matching condition, you need to impose this constraint, sometimes called weak section, on the fields and also on the gauge parameters. And this theory also has the properties you would expect of a gravity theory. So you have a kind of double diffeomorphism, which comes straight from string theory. Well, with some redefinitions, eliminations of auxiliary fields, etc., etc. Okay, and the entire thing is also ODD covariant, where, I guess ODDZ is the T-duality group for a D-dimensional torus. Okay, so this is actually the state of the art, like in this direction. Like, not even the quartic theory is known. Lots of people have tried, including some people, most of the people in this collaboration. It's really tough just to even construct the quartic order. Like, you could take this Lagrangian and you could say, well, maybe I can just write down all of the terms and work out, deform the gauge invariances, use another method kind of thing. It doesn't seem to work, and it doesn't work for some specific features that this theory has. The first is this weak section constraint, which comes from the string field point of view. You need to basically have a combinatorial explosion, because any term you might write down, you need to add the various permutation of this, where you project down to this locus on every possible term. So it's pretty tough just doing it by hand, and to start with. And moreover, there is also the expectation that you may have to switch on some strange sign factors which involve momenta and winding of, here I wrote it in the form where it appears from a specific string vertex, where you couple different string states, and the sign factor involves states from, say, the momentum of one state and the winding of another state. Okay, and these appear already in the string field theory on the torus, and if you don't have them, you fail gauge invariance and you fail the symmetry of the vertex. The theory is a bit nonsense. And these people found this in a brute force way, because back in the day they just produced the vertices for string fields in a way that's a bit unclear now that we have Riemann surface technology. What did I want to say about that? Okay, I'll proceed. So if you use this new machinery, which I've been working on, then you don't have to consider such things, because nowadays we have a better formulation of string field theory, definition of string field theory, where we know these things are resolved, and we can run the machine of homotopy transfer, and then this does all the work for us. Okay. So I'm going to explain what the algebraic structure, outline, what it briefly looks like. So basically you have, you start with something like a Lie algebra. You have a vector space and you have a binary bracket, and then you deform it by the addition of a bracket of one argument, this the operator, and it squares to 0. And you also add brackets that take any number of arguments, and then you deform the Jacobi identity by these new brackets over here. And then you also have Jacobi identities for all of these higher things as well. There's a very compact reformulation of this, but it's a little abstract, so I stuck with the sketch over here. And so mathematicians tell us you should think of this as Lie algebra up to homotopy, where homotopy is, you deform things by the exact terms. And this is because there's a relation to algebraic topology, where you take your space, you assign an L infinity algebra, and that's homotopy invariant. But for us, this the exactness just means up to gauge if you want. People can and have made this precise. And there's a general dictionary between infinity algebras and field theories, at least for Lagrangian field theories, and which was developed by Olaf and Martin in 2017. And Olaf is also talking about this on Thursday, I think. And basically, it tells you how to put the space of fields, the space of equations of motion, gauge parameters in a chain complex, and how to translate, if you have a Lagrangian, everything you know about the theory originally to an L infinity algebra. You can also go back and forth if you want. And the reason this is important in this context is that string field theory is only known in this description. In fact, it was the original example, and the entire concept of L infinity algebras was not really understood or noticed before Barton and Zwiebach wrote down closed string field theory. And here are the ingredients that enter the L infinity algebra are the things we are familiar with. Well, some of the things we are familiar with from worldsheet first quantized string theory. So for example, the bracket of one argument, D is the worldsheet BRST differential. So you see already that you take the cohomology of that, or you take the exact things, and this is related to physical and unphysical states of the string. And then the vertices, I'm not going to tell you how to construct them because it's quite an involved proof. But they exist. And then there's also a bracket structure, an inner product on the algebra that makes it cyclic, which corresponds to a construction involving the conformal field theory, the inner product of states over there, the BPZ inner product. And so the basic claim of covariant bosonic string field theory is that you can take your CFT, and here I just need it for tree level. You can take your CFT, and then you can take a partition of your moduli space, and out comes a collection of brackets B1, B2, B3, etc., that make the entire thing into an L infinity algebra. And you can go back and forth from this to the quantum master equation. Oh my God. In front of it, okay. Okay, right. I'll stay from here to there. Right. So if you have an inner product, you can go back and forth between this formulation and a BV or quantum master equation. Right. And for closed string fields, in fact, you need an infinity algebra because of, how the moduli space works there. For open string fields, you can also have a homotopy algebra formulation, but you can just take all of the higher brackets to be 0. Right? It just looks like an associative algebra. And the theory actually looks like Chern-Simons theory. So this is for the covariant theory, that you need an infinite number of brackets. However, there exist equivalent Lycombe type theories for some backgrounds, at least. For example, the theory by the Kyoto group, which can be cubic. Yes, so cubic theories correspond to Lie algebras, with a differential and some grading by ghost number in this case. So if this is really, so if these infinity algebras are really to be something physical, and we have two equivalent descriptions of the same object, which is closed string field theory, and one has an infinite number of brackets and the other just has 2, then we need a kind of equivalence of these things such that, the two algebras I just described, which look very, very different, are equivalent to each other. And this is in fact known and was invented by the mathematicians in the 90s, Stashev and Kontsevich, I think. And so the difference is, so firstly, you start with something that looks like what you would have in a Lie algebra context. You have a linear map involving the two spaces, phi1, which takes one argument from one space where the infinity algebra lives and maps it to the other. And the property for this homotopy equivalence that needs to hold is that it preserves the cohomologies under the D, which is, for string field theory, it's the worldsheet BRST differential. So this is, we can identify this with a physical notion. And then you also have a nasty tower of linear maps that take any number of things in the first space and map it into something in the second space, and then you have some identities involving all of these in the brackets. Again, there's a compact way of determining what these are, but I won't bore you with the details. So we come to what I call the homotopy transfer construction, which is, say you have an L-infinity algebra on your vector space X, and then you have some vector space Y. Say it's already a chain complex, so you've put a differential on it. Fine. And then you have a map phi1 that satisfies this condition. Then the claim is there always exists a construction of higher brackets B2, B3, etc., that turns Y into an L-infinity algebra that's equivalent to the first one. And this is an algorithm. It's not unique. So there's lots of ambiguity in this, but all of the outputs, well, they're all equivalent. So nobody cares. So if the other space Y is a subspace of the original space, which is the case we're interested in, right? We want to see, when to take string field and want to truncate to the space of at levels n equals n bar equals 1. Then the input includes a linear map on the original space, which is a homotopy, which is called a homotopy, and it satisfies this relation. So P is the projector onto the space as the state we want to keep, the effective degrees of freedom, and then D is will be the BRST differential. Oh. Okay. Nope. Yes. And then 1 is 1. So what I can tell you about this is that the conditions for showing that this transfer exists and for calculating the resulting structure, they only involve the free theory. So for our purposes, we only need to look at what the worldsheet BRST differential is doing, which is, it's a torus. We know what it's doing. and then the projector to the state we want, which is fine. And then there's just this homotopy map H. So if we can find a linear map that does this, then we have one. And we can find a linear map that does this. Oh, thank you. We can find a linear map that does this, and you can view sense construction of effective field theories of strings in terms of an ansatz for this homotopy map. And this is a very simple ansatz. So you just take the propagator G of string fields, for example, Ziegel gauge propagator, if you've seen such things. And then you take a projector to the complementary states to the effective states that you want to keep. So if you want, you can view this as Feynman diagram construction, where the effective vertices are built from the original ones connected with propagators involving the complementary states, the states you don't want to keep. And this is how he formulates it. Right, so as I keep repeating, for string theory, the differential is just the BRST differential. So the $2 million question is, if we take P to be the projector onto the states at level n equals n bar equals 1, which for flat space, Minkowski space string theory, they give you the graviton, the dilaton, and the other fields. Can we find an H that works? And the answer is no. At least not if you start with bosonic string theory. However, what we can do, at least for generic torus moduli in Euclidean signature, we can take a projector to just the states we want and the tachyon. And that's it. And the reason for this is basically that in Euclidean signature, the cohomology, or something slightly bigger than the cohomology, depending on details that involving the propagator and the gauge fixing that I don't want to go into here, it's strictly contained in the subspace. So we have that this property is preserved by Y, where here Y is the image of the projector. So we can run the machine of homotopy transfer, and now it comes a theory that contains double field theory and interacting with the tachyon. And so the first check we can do on this, so I should mention that we know what the resulting brackets look like to all orders. Like we wrote a paper last year where we have very explicit, very general formulas. And lots of people have explicit formulas for these things. So there is a recipe. It's very ugly, but you know, it exists. I'm not displaying it because it's not very photogenic. So if you have this resulting theory, the first thing you do is you check whether to cubic order the obtained theory agrees with what was derived in 2009. And yes, of course it does. And it does modular elimination of auxiliary fields, which is fine because, you know, elimination of auxiliary fields is also an equivalence of homotopy algebras, as you would expect. Anything that's kosher and takes one field theory to another field theory, which is physically equivalent, is an equivalence of such things. This brings me to the end of the talk. So what we have is a machine that constructs all of the vertices of this DFT plus tachyon theory, starting from whatever vertices you have for closed string field theory, bosonic closed string field theory. And this is a nice application of this very general homotopy algebraic technology. And it's notable because in this instance, we couldn't even construct the next unknown vertex, which is the quartic vertex. Here we just get all of them. And this is still not this is not quite the thing we want because, well, for one, we still have the tachyon. There's at least two resolutions to this one can conceive of. For example, there's a notion of consistent L-infinity truncation, which we mentioned briefly in the paper I was talking about. So that can remove the tachyon, and this is a kind of stronger notion of the consistent truncation you may be familiar with in the context of supergravity, which says that solutions of the truncated theory automatically solve the original theory. And this is realized through an injective element dimorphism. So if this exists, and you know, this is something you can in principle now calculate, at least to any finite order you want, then we have one. And the other, of course, the other way to remove the tachyon, which is the probably more physically reasonable one, is just to start from superstring field theory. And this appears to have been invented actually quite recently for type 2. And it seems to have an L-infinity algebra structure. We didn't quite do it that way because one thing which is slightly unclear in this L-infinity algebra formulation is what is the correct definition if you want to go super for a technical reason. Essentially, where do the minus signs go? So everyone suspects they're all equivalent, but you know, I don't quite know yet. So I don't want to speculate that you can use the exact same argument to automatically get exactly the thing we want. I don't do things like that. So the big question here is actually, what exactly is this thing? So we constructed a thing which you know, is consistent, engaged, invariant, manifestly doubled, but we constructed it in terms of the vertices of closed string field theory, which are not known explicitly. We have a definition for them, which was given in the 90s, and it's perfectly rigorous, and the things exist, and they satisfy the L-infinity algebra identities. But how do we display one of them? I mean, I know we can display, say, a quartet vertex, but say we want to go to 6th order. I think like nobody has ever written down such a thing. So it's not clear that the nice property of the action over here. So this is not just, you know, it doesn't just exist and is consistent. Oh, okay, I'll wrap it up. But it's also nice and local. If it's not local, at least in double spacetime, then you have a big problem, and it's a bit nonsense. So yes, so we need to determine whether this locality holds. And then, of course, there's the question of background independence. So if you have this setup, then you set, say, all of the Weinecks to 0 or all of the momenta to 0. But you don't commit to a choice. You consider all of the ODD equivalent choices, and then you get a strong constraint theory, which is not quite double, but it's still ODD covariant. Then this theory is known to all orders, and it's background independent. So is this a hint? Does this actually remain true in some way? Is this a way to examine issues of background independence in string theory? And with this wild speculation, I end my talk.
Other questions? No, Larissa?
Thank you, Alice, for the talk. So I will start with your wild speculation about background independence. So in the old paper of Spivak from '92, he's saying that in L-infinity algebra, you can sort of achieve this background independence through inclusion of the zero map. The problem with inclusion of the zero map is that I'm not sure that then you lose the chain complex structure, and I don't know how to do the homotopy transfer. But I think this would be a way to go, because I think in mathematics they might know. But inclusion, well, he argues that this would lead to background independence for the closed string field theory. Did you discuss this at all?
No, we didn't discuss this at all because, well, as you say, you can't, it's not entirely clear whether you can do all of this homotopy equivalence if you don't have strong homotopy Lie algebra, which is the kind I just talked about. So.
What you called here homotopy equivalence for me is just L-infinity morphism. But this L-infinity morphism can include a constant element. It exists. It's curved L-infinity morphism. This thing exists in this respect.
Yes.
I just don't know how to transverse the structures.
Yeah, exactly. Yeah. Yeah. So it doesn't work anymore. Oh dear. Okay. Yes. So to clarify, the thing here is, yes, it's an L-infinity morphism. You can have that in your scenario, of course, but you don't have this condition. This is really what powers this entire construction.
Yes.
Because it vaguely looks like you have some equation, which is the Jacobi identity, and the offending term is just something that's declosed. And if you have an equivalence of cohomologies, you can find something that's the exact in the appropriate subspace, and then it, boom, works. But otherwise, I don't know.
Thank you.
Okay, no more questions? None from the online participants, right? Yes, I cannot see anymore. No. Okay, so we can thank Alex again.
Thank you. Here you go.
front, left, front, right, front, left, front, left, front, right, front, left, front, right, front, right,